natural base of the logarithm, we use this e. We call the natural base of the logarithm or Napier's numbers because Napier discovered these numbers. If you consider these functions, 1 plus 1 over n, and the power index is n. If you substitute n equal 1, it becomes just 2, because 1 plus 1 is 2. If you substitute a 2, it becomes 2.25. And then substitute 10, it's increasing. It's an increasing function. But actually, it's convergent functions. It's convergent to the finite numbers. So it's convergent. 2 becomes a 2.71828 blah 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 blah. So this is what we call the Napier's numbers. Using these Napier's numbers, we can define the exponential functions. Y equal exponential x. In this case, e is larger than the 1. So if you substitute x equals 0, it becomes 1. If you substitute x equals 1, it becomes e. So it becomes 2.7 blah blah blah. So it's larger than 1. If you substitute x equals 2, it's e squared. It's larger than the e. So if you substitute x or the x, you can draw the curves. This is the exponential functions. From this exponential function, we could actually define the logarithmic functions. So this is y equal exponential x is a logarithmic function. Then we can convert the x and y. So substitute y equal x, and this is x to the position the y. So x equal exponential y. And we would like to express the y equal some function. Y equal this function. And we introduce this log function. This y equal log x exactly same with this function. Okay, then we can draw the curves, logarithmic functions. If you substitute x equals 0, it becomes a 1. If you substitute x equals e, it becomes 1. E squared, it corresponds to the 2's. Okay, this is a log functions. And the law of the logarithm. So I'd like to prove that this one. So when you consider the logarithmic function, y sub 1 equals log x1, y sub 2 is log x2. You can express the x sub 1 is exponential y sub 1. X sub 2 is exponential y sub 2. Then product of the two functions x sub 1 and x sub 2 is expressed the exponential y sub 1 times exponential y sub 2. You can express the exponential power index becomes the sum of the y sub 1 plus y sub 2. Then we'd like to take both sides of the log function, log and the log. So this is the next line. Then from the here to the here, we are going to use this relation. So to prove that this function, we just start using this one. Exponential p is equal to the exponential p's. We'd like to express this p is gonna be log exponential p. So in the case of the logarithmic function, log e to the p is equal to the p. So we use these relations here. So in this case, log exponential y sub 1 plus y sub 2, this corresponds to the p. So we can express the p, y sub 1 plus y sub 2. So substitute, return to the original equation back to the here. So it becomes log x sub 1 plus log x sub 2. So product, log function of the product of the x sub 1 and x sub 2 becomes the sum of the log x sub 1 plus log x sub 2. With the same technique to prove the next formulas. So also again, same starting with here, and then we can express the x sub 1, x sub 2 using exponential function. And then now x sub 1 over x sub 2 can be expressed exponential y sub 1 minus y sub 2 and substitute. And then again it becomes, we can express log x sub 1 minus log x sub 2. And then finally, last formulas for the log function. Starting equation exactly same. Express the x sub 1, x sub 2 with the exponential function. We consider x sub 1 to the p. So you can substitute this x sub 1 here. Then exponential y sub 1 p. So it becomes exponential p, power index becomes a p times y sub 1. So we can take a log in the both sides. And from the log exponential power index is going to be just we have a power index. And substitute, return back to the here. Then we discover log x sub 1 p is equal to the p log x sub 1. Okay, so often we use these three formulas for the calculation in physics. Okay, this is the end of this session.